video, I want to introduce you to C programming for the PIC microcontroller. This will only serve as a brief introduction and help to get you started, but will give you some of the fundamentals of how C programming works and how that compares to PIC assembly. So up to this point in the course, we've been using assembly primarily to program our PIC microcontrollers. Assembly is very low level, as you have seen. You don't have native things that you might expect in a programming language, such as if statements, for loops, while loops, things like that. The good news is now we get those back. The good thing about assembly, though, is that really helps you to figure out exactly what's happening at the processor level, at the individual register level. And some of those details do get abstracted away when you're using a higher level programming language like C. And so your code, when you write it in C, it will actually get converted into the native assembly commands that we've already been using. And it may or may not be the most efficient. So one of the things that Microchip does, Microchip is the company that makes the PIC microcontrollers, and they also are the ones who provide MPLAB and their various compilers, such as the XC8 compiler that we're going to be using. They have a free version, and then they also have premium versions of their compilers that they charge more money to use. And if you just use their free version, they will convert your C code into a usable code, but it may not be the most efficient code. So you may need to actually try to optimize your code a little bit better. You may actually be able to get more optimal code writing it in assembly rather than writing it directly in C. So that is an important consideration as you think about writing C. But for our purposes, we're going to go through some simple examples over the next several weeks in the course, and you should get a good feel for how programming in C works. So here are the basic components of a C file. You'll have include statements. This will include the appropriate libraries. We did have one include statement in assembly. It'll be a little bit different in C. You'll have config statements. So if you remember, we just had that big configuration block at the top of all of our assembly files to get them to work. We're going to have a similar configuration here, which will just configure how our microcontroller is functioning, but the format of that in C is going to be very different. One thing you're going to do that we haven't done before is you're going to define your clock speed. This will be very important because, as it turns out, in C we actually have delay macros. So in assembly, you actually had to write your own delay, or you had to know what to write out to timer 0 and things like that. Now in C, you can take that to a very high level and just say, I want you to delay for X number of microseconds or X number of milliseconds, and it actually figures out how to do that delay, whether it's using the internal timers or it's using a delay subroutine that it would write. And so that is all based upon the clock cycles that it is using. As you know from using our analysis of timing, we based it all on a 1 microsecond clock cycle. Well, that's really because we've been using a 4 megahertz crystal oscillator. It gets divided by 4, and so it's really operating our instruction clock at about a 1 megahertz frequency, and so you get 1 microsecond for every instruction cycle. If you were to use a faster or a slower clock, then you would have to scale up or down your timing analysis accordingly. Now with C, all you have to do is define your crystal oscillator speed at the top, and then it figures out how to do all those delays for you. We'll talk a little bit more about that later. You can also define aliases just like we did in assembly. There'll be a little bit different syntax for how to do that. So you could have an alias referring to your RS, RW, and E, and then if you chose at some future time to move those ports to somewhere else, then you could just update your alias, and that way you don't have to update the rest of your code. We'll talk a little bit about function prototypes. Functions are effectively like subroutines. Prototypes tell you about what those functions are capable of doing in terms of returning values and accepting values. We'll talk much more about that later. And then you have one main function. That is effectively what's going to be orged at 0. That is what's going to happen upon restart. You're going to start executing in main. And then you can have other functions defined down below, including an interrupt service routine that we'll define as a function. So let's go ahead and unpack this and start talking about the different things that you will have inside of a C code file. So the first thing that is important, you're going to need this in order for your code to work at all, are the include statement and the config statement. This whole block of code can actually be automatically generated from within MPLab. And so I will show you how to do that. There are some drop-down menus. But effectively what's happening here, because we are using the C compiler, and it's the XC8 compiler, we're including xc.h. So that just includes all of the appropriate variable type definitions, internal functions, macros that we'll talk about later, and just says, hey, I need all these utilities to be able to use the XC compiler. These config statements are doing exactly the same thing as the large config blocks that we used in assembly. So for example, this is saying the oscillator is a high-speed crystal oscillator. We are not enabling the watchdog timer, so that is turned off, and we've got several other things like the master clear enable is on. That's allowing us to use RE3 as a master clear. That enables your blue reset button that you have on your trainer kit. And then we've got things like code protection, data protection, what to do if you have a brownout, which is basically if the voltage coming from your USB port that's powering this ever dipped below 4 volts. Are you enabling it to reset code under that circumstance? And at what voltage? In this case, the voltage would be 4 volts. And you've got a few other things that we just don't need to worry about. So these will be generated for you. You don't have to write this code. In fact, for a lot of your code, you could just copy and paste this in there if you didn't want to automatically generate the configuration block. Clock speed is defined this way. So you just use hashtag define or pound define underscore xtal, that's crystal, that's the short for crystal. So it's underscore xtal underscore freq, and then space, and then you type out the frequency of your crystal oscillator in hertz. So we're using a 4 megahertz crystal oscillator, so we put 4 million. Don't comma separate your 4 million, so it's just 4 followed by 6 zeros. That will define our crystal oscillator speed. That will be very important for the lab that we're going to be doing next week, which will be relying on some delay macros. Aliases are defined this way, so these are the pins that we're using for our LCD. So our RS pin is attached to port A bit 1, so that's RA1. RW is attached to RA2, and E is attached to RA3. You'll notice here that I'm not specifically saying port A, comma 1. You can in C now directly refer to each of those pins. So each of those pins and each of the particular bits of your special function registers have a unique pin name. And so you can actually refer to just the pin name and not even worry about what port those are inside. So you can define RS as RA1, just doing these define statements. So that's useful. You might have other things that you define as an alias. So you might say push button. So define push button, and then you could say whatever pin your push button happens to be attached to. Or you might have a light, and you might just define light as whatever port the light happens to be attached to. And you can just use very similar syntax. This is generally up at the top. After your config statement, then you can put in these define statements and just define whatever aliases you want to use. The main function is what starts running after you reset or cycle power, and it does run in an infinite loop, so it will just continue to go, and if it goes all the way to the bottom, it'll just restart back at the beginning. Typically, what we're going to do is actually create an infinite loop inside of main, and so what that will mean is we'll do some setup, and then there may be some things that we want to do over and over and over again after we've set some things up, and we don't want to go all the way back and reset things at the beginning. So we might just set up things like our ports, set up our LCD, configure that, and then there may be some things that we want to run over and over again until we cut the power out. So you might think about things like industrial equipment or automobiles. If you had things like that, there are things that you want them to run in an infinite loop. And so that's a pretty good thing for a lot of systems to do, is continue to check this until I turn off the system or until I reset the system. You can only have one main function, and it's a good idea to try to keep your main streamlined and then to offload the other things that you're going to be doing into other functions that you will define. That allows us to do some compartmentalization of the other actual features of our code, and so a little bit of abstraction. And that way you can also do some iterative testing. So instead of just checking your whole main to see if that works, if you've divided up your different tasks that need to be done with your microcontroller into various sub-functions or subroutines in these functions, then you can just test to make sure this function is working, the other function is working. So things like writing data out to an LCD, you could write a function to do that, or checking a value coming back from the keypad, you could write a function that would do that. And so it's a good idea and good programming practice to divide up your code into various functions and just test them one at a time. So here's the basic syntax for main. We're going to say void space main, and then we'll have an open parentheses and a closed parentheses. Then we'll have an open curly brace, and then whatever main needs to do will go in here, and then we'll have a closed curly brace. This void indicates that when this function terminates, it's not returning anything. Nothing is going back. In some cases, if you've taken a C programming class before, you may have seen int main, and so in that case it returns an integer type, and generally what happens there is it either returns a 0 if things all executed as they should have, or it might return another value indicating that there was some kind of an error. In this case, we're just going to use void main and not worry about returning anything. If you've already taken any other C programming class, you may note that sometimes you have command line arguments in here. That typically helps if you're writing C programming that you could just invoke a program from a prompt. In this case, this is just running based upon power cycling in, so there's no real good way to input command line arguments. We're not actually executing this from a command line, so in this case we will not put in our ARGV and ARGC if you're familiar with that. If you're not familiar with that, just don't worry about it. I just don't want to confuse those of you who may have a C background prior to reading these slides and watching this video. Variables. So one of the things that we did in assembly is we declared some variables. They were typically all 8-bit values, and we defined a memory location. We used that EQU statement to equate our variables to a particular memory location. In C, we're just going to declare a variable type, and we actually have some different options on our variable types. We'll talk about those in just a moment. But the compiler itself actually handles allocating the memory. So you don't have to worry about this integer and this other integer happen to be in the same location, any of those conflicts if you've ever had that problem. Effectively, all you do is say, I want a variable, I'm going to call it this, and it's going to have this type. You can also initialize that value. So here's an example. You could just type int myInt, and then if you put a semicolon, semicolons are important because that terminates every statement. You're going to need those after almost every statement, with some exception, as we'll talk about in just a little bit. But this first line just declares an integer variable named myInt, and it will just assume some default value. It will generally not assume a default value that you want it to have. So if you want it to start out at 0 or some other value, you need to initialize it. So here is in one line how you can initialize and declare a variable. So this will declare an integer named myInt, and it will start it at a value of 9. There are various integer data types that you can have, so now you can actually make the most use of the 8 bits that you have in a register. So you can actually declare a single bit, so that will just be a single bit. Before, we had some other variables that we declared, and really, even though we were only using 1 bit, we had to assume we had all 8 bits. So an example of that was our run variable that we were using when we had our stopwatch lab. So in that lab, you had a run bit, but you were actually using an entire register of 8 bits. Now we can just declare that as a single bit, and it will just be 1 bit wide. Amongst your 8-bit values, you can have a signed char or an unsigned char. The reason that is char is because that is typically used to hold characters. So if you remember the ASCII values that we were putting out to displays, those were characters that were showing up on our LCD panel, and each of those ASCII values was only 8-bit wide. And so typically, if you're going to use a character, that is going to be 8 bits. You do have the option, if you're going to have values that can be held within 8 bits, so anything between 0 and 255, you can declare them as an unsigned char. So unsigned chars hold 0 or positive values between 0 and 255. If you have a signed char, that actually uses 2's complement 8-bit values. And so if you remember back to your digital class that you took last semester or whenever you took it before, you can use 2's complement to represent both positive and negative values. That, of course, limits how large those values can be, but it now opens up the palette of negative numbers. And so in all of our programming to this point in assembly, we never used negative numbers. Now we can actually use negative and positive numbers, which will be quite nice. If you declare something as just a regular unsigned or signed, you can have 16-bit values, you can have 24-bit values, and you can have 32-bit values. Effectively what that does, even though we're still using an 8-bit architecture, is it will actually spread that integer value across multiple 8-bit blocks. And so you'll have multiple memory locations. In the case of signed shorts or unsigned shorts, signed ints, unsigned ints, those will take up 16 bits. So that allows you, in the case of signed values, to have negative and positive values. In the case of unsigned values, 0 all the way up through 2 to the 16 minus 1 in there. So that should get you most of the values you would need. But if you need bigger values, there are what are called longs, short for long integers. So those allow you 24 bits. And then we also have, this is kind of a funny name. It's a short long is 24 bits, and then a true long or long are both 32 bits. In some architectures, you may even see longs as being 64-bit if you have a 64-bit operating system. But the biggest we have here inside of our PIC is going to be 32-bit, which will be plenty large for any values that we're going to be using. You also have, here's the various ranges. So for the bits per character or bits per char, you have 8 bits. Max value of a char is 127, minimum value negative 128. That shows the range of 8-bit 2's complement values. You can go all the way down to negative 128, all the way up to positive 127. So chars and signed chars actually are really basically the same thing. So they have the same range, same number of bits. Unsigned chars allow us to get between 0 and 255. If you have a short, same thing as a signed short, that allows you between 32,767 all the way down to negative 32,768. Unsigned short allows you to get up to 65K, 65,535 to be more specific. And then you can see the other values. So down here, when you get into longs, you're talking really large numbers. Unsigned long, even bigger than that. So now we're out to values up to about 4 billion. So that should be plenty large for what we're going to need to do. Floating point. So now here's something else that we have not used before. You now have the ability to use values that are not integers. And so in this case, you could have 23.5, 52.8, whatever it happens to be. And so these will use floating point arithmetic. And you can actually specify whether it's 24 or 32-bit. So if you remember back to your digital electronics class, we talked about floating point and how those are represented. So where you have a sign bit, you have your exponent, and then you have your mantissa. You can actually hold those within 24-bit, or you can extend them up to 32-bit. And so we have floats and we have doubles. Floats allow floating point. Double traditionally was called double because it allowed for bigger values, but as it turns out in PIC C, doubles and floats are really exactly the same. But in this case, you do have options, and there's compiler options as to whether a float or a double is 24-bit or 32-bit. For our purposes, 24-bit will be just fine, so we won't need to extend up to 32-bit to get that extra precision. So, variable declaration is a very important thing to learn in C. Variables now have scope, and so scope is something that's very important to learn about when you're talking about C programming. Before, when we used an EQU statement in assembly to declare a variable, that was just declared as that memory location, and that was used anywhere we wanted to use it. So we could use it inside of our main loop. If you had a goto, you could use it down there. If you had a call to a subroutine, the subroutine knew about it. Now, variables that are declared inside of main, for instance, are locally scoped to main. And so if you call a function, what you need to do is pass that variable as an argument to that function. We'll talk about more of that later. Or you can declare a variable as globally scoped, and what that means is now it's available inside of main, it's available inside of any other function that you may call, and so any of the functions that you use can actually manipulate that. Some people who teach C say, oh, you should avoid global variables. That's not okay, because they want you to get in the habit of passing variables from one function to another. You can also, when you pass variables to a function, you can pass them by reference, which means if you change them down there, they actually change the variable itself. Or you can pass them by copy, which basically just says, hey, the value of this variable happens to be 17. And then if you manipulate it inside the function, it's still 17. You're not actually manipulating the value itself. So here are some examples of how to declare variables. Here's an integer I, and we're initializing it at 0. Here's an int I, has no default or has no initial value, just accepts a default. Here's a double, we'll name pi. You might want to actually do pi with a constant, but this shows you an example of how you could define a variable named pi out to however many decimal places you want. Registers and bits. And so in C, you now have access to all of the registers that we've been talking about before. But one thing that's going to be very different is you're not going to have to use W and status nearly as often. So what that means is you can still read from W and from status, but you're not going to need to write to them. Before, when we wanted to put anything into a particular register, we had to put a literal value into W and then move that into the register itself. Now you can just say this register equals this value. It happens directly with one assignment. So for example, if you wanted tris A to equal FF, you can just write it this particular way. Tris A equals 0xFF semicolon. You don't have to move FF. You don't have to get into the right bank, so you can talk to tris A. It automatically knows, hey, if you're talking to tris A, you better be in bank 1. And so it changes your RP0 and your RP1 automatically for you. You can directly address a single bit. So you can say RB0 equals 1. You can also copy in the value of a register into a variable that you've declared. So if you don't want to manipulate what's on port C, but you do want to take in its value and be able to process that, this would be effectively the same thing. This last line, my variable equals port C, would be the same thing as making a copy of port C, putting it into the W register, and then moving it from the W register over to your variable that you've declared. Now we can do all of that within one line. Functions. Functions are very similar, if you took a MATLAB course previously, to what you did in MATLAB. They have a return value and they can take in 0 or more arguments. And arguments basically allow it to process based on some values you put in. So you might have a function that calculates the area of a rectangle, and in order to calculate that and return it back, you might return back the area and you might take in a length and a width. And you might decide what the types are of each of those. So depending upon what you're actually calculating, you might not need to return anything at all. You might need to return an integer. You might need to return a floating point value. So if you're talking about the area of a rectangle, perhaps you're going to restrict your rectangle to just have integer sides, in which case the area is going to be an integer. So you might declare int area and then have 2 integer arguments for length and width. Maybe you want to open it up and allow any value, so you might have float area, so float being the return type, area being the name of your function, and then you might take in 2 floats as the length and the width. You might have some things that don't need to take in arguments, don't need to return anything at all. I'll show you an example of that in a moment with doing things like initializing an LCD. So the main difference between functions in MATLAB and functions in C is that in C they don't have to be in separate files. So in MATLAB, when you declared a function, you had to have a separate .m for each function that you were using. Now in C, we're going to declare our functions within the same .c file as we have our main function and our other config statements and those types of things. Main is also a function, so it's important to keep that in mind. So how do you write functions? They're very similar to subroutines, but you don't have to remember the return statement necessarily. You can have returns just to get back, and you can return particular values. If your function does return a value, that could be opening up the palette a little bit more, a literal constant value, or it could be you could return a value based upon a calculation. So in assembly we had RETLW to return with a literal value in W. You can actually just return L times W, length times width, something like that. Functions are useful if you have repetitive tasks. They take in, as I mentioned, 0 or more arguments. They may return a value. They might be void if you don't need to return a value. And if it is returned, you have to say, is it an integer, is it a double, float, whatever it happens to be. Function prototypes are also very important. So what's going to happen when your C compiler runs is it's going to take in some information in main, and in main you might call some other functions. Well, if you haven't defined your function above main, it's going to get there and you're going to have a call to this function. It's going to go, well, I don't know what that function's supposed to do. But if you have a prototype up above main, it tells you, okay, there is a function. It's going to be defined somewhere else. It has this name, it returns this type, and it takes in these arguments. And so then it says, okay, I understand there is this function. I'm going to look for that later. And so prototypes are basically one-liners. They're usually the same as the top line of the function followed by a semicolon. We'll see some examples of that later. So here's how you call a function. You invoke the name of the function, an open paren, and then you put in any arguments that that function takes in. So if you had a function named myfunc, you would just say myfunc, open parentheses. If there were no arguments, you would just immediately put close parentheses and a semicolon. In this case, we're going to take in two different arguments. So perhaps we're going to send a constant 4 in there. We might also have a variable x that's going to be sent in there. And so depending upon what those are, the values that we send better be compatible with the arguments that we've told it. So for example, if we say a function is going to take in an integer and x happens to be a float, it will have to round those. It won't give you the desired results. So here's an example function. This is a void function. As you can see, LCD init. And this is doing all those initialization sequences that we have for the LCD. So we're doing things like clearing the screen. So we're directly putting 1 into port D, and then we're calling a function LCD enable, which is just going to send out this instruction. And instruction 38, that sets up 8-bit mode, 2-line display, all these kind of things. And so we're just setting all this up, and then once we're done, we're just going to return back to where this was called. There's no need to put a return statement. Once it's done and finishes executing this, hits this curly brace, it's going to go right back to wherever it was called. Notice also there's no arguments being passed in here, so we're just executing LCD init. This should run one time and just clear out our display, set up all the options that we want for the LCD panel, and then be done with it. You'll also notice over here, this is how you put comments in C, 2 forward slashes, and then whatever is after that gets ignored in the rest of that line. Here's our LCD enable function. In this case, this is relying upon those aliases that we already had. So RS being 0 says it's a command, it's not data. RW, we're writing, not reading. And then this E followed by the delay and E going to 1, that is your rising edge clocking it. And then delay here would be another function that you're calling. So in this case, you could be 3 layers deep right away. So we're calling LCD init. From that, we're calling LCD enable, and then from that, we're calling delay, which may or may not call another function. Keep in mind, it's very important to track how many calls have happened because we're still using the stack here. That allows us to return. And so if you have a function calling another function, calling another function, if you get 8 layers deep and you haven't returned back, you're going to have a stack overflow. So it's very important to track that. Interrupts are also available in C. The main thing here is you just add this keyword interrupt. When you're declaring the subroutine, it is a void type, and just put ISR, and then there should be no arguments passed in because you don't know what the values of those variables would be and what particular variable should be sent in. So this, you put in your code to handle the interrupt event, and then we'll just put a regular return when we're ready to go back. So typically interrupt service routines, you don't have to worry about, in this case, saving the W or the status register. Those are automatically saved. But the interrupts are a special type of function. They can't accept arguments because you're not explicitly calling those. Those are called because some particular interruptible event has occurred. If statements, yes, you get those back in C, so that's nice. And we have a couple different options. You can have if and then inside of parentheses whatever your condition is, followed by a single line. If there's just one line of code you want to execute when this is true, then you have this. Otherwise, if it's multiple lines, you have your condition inside of parentheses, and then do this, then do this, then do this. Notice there's no semicolon after the if. The semicolon, the full statement would be if, open parentheses, condition, close parentheses, then what you're going to do, and then the semicolon. So very important to note, don't put a semicolon right after your if. And if you need multiple lines, you can just put them inside of curly braces like this. And there's no semicolon after the curly brace either. All right, so here's some examples of if. If our value in port B is equal to hexadecimal 7, and notice double equals is what we're using to check for equality, then I want to assign one more into count. So count equals count plus 1. There actually are shortcuts in C, so you could actually say count plus equal 1, and what that would do is say count should equal the current value of count plus 1. That's shorthand for what we have right here. You can also, here is a multi-line thing. If we wanted to check to see if port B is equal to 9, count is going to equal count plus 1, and port A is equal to 0. You also have the capability of doing else if and else. So if this is true, then do this, else do that. You can add an else if and have a similar conditional in there as well. Loops, we do have real for loops and while loops again. So that's a nice thing. Here is the basic syntax of your for loop. For, open parentheses, an initialization of a value, a conditional on that value, and a modification. So this says declare a variable I. It's going to start at 0. That's going to be our loop counter. So long as I is less than 100, every time we pass through the loop, we're going to increment I. So I plus plus is shorthand for I equals I plus 1. Then every time you go through this, you're going to increment or do whatever it is you're going to do inside that loop. So in this case, you're going to do whatever you do, and then I gets incremented, then you check the conditional again. So this is going to start out with I equals 0. You're going to run whatever's inside that loop code. Then you're going to increment I. I is now 1, and you're going to say, wait, is 1 less than 100? Yes, it is. So you're going to run it again, increment it to 2, then check back. Is 2 less than 100? Yes, it is. And you're going to keep going until you get to 100. Now 100 is not less than 100. You're going to escape out. So this loop will actually run 100 times with I starting at 0, going all the way up through 99, and then once it's incremented to 100, it'll escape back out. Just like the if statement, if your for loop is only doing one thing every pass through, you don't need the braces. But typically, with for loops, we're going to do multiple things. So we might have various lines of code inside of these curly braces. To run code while a condition is true, or you can do while a condition. You can also run something while something is not true. You just put an exclamation point in front of it. That is the symbol for not. So while not this value, or while this particular condition is true. So while port A is less than 3, or while port B is greater than 7, do whatever it is. You can also create an infinite loop while 1, so logic 1 is considered a Boolean true. So while this is true, and 1 will always be true, you can just do something over and over again. So this is useful after you've set up some things like setting up your LCD, setting up your ports as inputs, outputs, etc. Now you can get in there and just say, okay, from now on, just run this in an infinite loop. Do whiles. This allows you to run code one time and then check the conditional. It's very similar to a while loop, but with a regular while, there's no guarantee you're even going to run one time. So if that conditional is not true at the very beginning, it's never going to run anything inside the while loop. With a do while, you're guaranteed it will run at least one time, and then it will check the condition after the fact. So really the main difference between do while and while is that a while loop checks the conditional before running the code. The do while checks the condition after running the code. And so this is very similar in nature. It's just a matter of a do while guarantees you it will run at least one time. Arithmetic. So before we had addition and subtraction. Now we get division and multiplication back. So that's very nice. Division, you can use a slash. Multiplication, use an asterisk. So you can say port B equals port B plus 3. Port B equals port B times 5. All those things are back and available. You can also do other logical operations. So anding and oring, this will do these entire registers ANDed together, or you can AND together a couple conditional statements. So you can say, is this true and this is true and this other condition is true? If this is true or this is true, here's your not. If you want to use bitwise ANDing and ORing, it's a single ampersand or a single pipe here. And you can also do bit shifting. You can shift things to the left and you can shift things to the right. With less than, that'll actually take a value in a register and shift all the bits to the left. Or likewise with the greater than, you shift everything to the right one bit. We'll see some examples later on in the course as to where all of these are useful. You can also declare arrays inside of C. One thing that's very different in C versus MATLAB is arrays are indexed starting at 0. So your first element in your array in MATLAB starts at 1. This is indexed starting at 0. And also C uses these square brackets rather than parentheses. So you have to also inside of C tell it what the types are of those arrays. MATLAB is very flexible, and you can just declare an array and it could hold integers or characters or strings or whatever. In this case, you have to say this is going to be an array of integers. This is going to be an array of chars. And so you give it a data type, give it a name, and then you tell it how many entries you want in there. So this will create an array named myArray holding data type. Could be integers, could be chars, and there's going to be 10 of them. And they're going to be indexed starting at 0 going up through 9. So there's index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And to retrieve a value from an array, you could just have a variable named myVar. That's going to be one instance of that data type, and it'll just be myArray element number 7, which is actually the 8th entry in that array because we are indexed starting at 0. Then you're pulling that into your variable so you can actually do some processing on that value. So that ends our introduction to C programming, and we'll see some examples as we get into next week.